he likes to say that there are as many ways of doing amazing physics as there are amazing physicists. And that's absolutely true. And so I don't think there's one golden path.
Hey, welcome to Non-Standard Models. Today we have something a little bit different. It's going to be an unscripted interview that I shot at a conference back in December with the famous theoretical physicist John Joseph Carrasco. While still a grad student in the mid-2000s, he made quite the discovery. It was called the BCJ double copy, and it's since then spawned a thriving, vibrant field of its own. In fact, we already covered this topic in a previous episode with Professor Jan Plewka called From Atoms to Black Holes, but we thought it would be equally interesting to hear it from the man who discovered it himself. So there's going to be some technical terms in here. It's not going to be as beginner-friendly as our previous episode, but wherever possible, we've done our best to include little explanations at the top. So just look there whenever you're confused. John is an incredibly passionate and eloquent speaker, so we hope you'll enjoy this interview as much as we did making it. All right. Hi. Can you tell us your name and current position?
Sure. My name is John Joseph Carrasco, and I'm an associate professor of physics and astronomy at Northwestern University, which is just north of Chicago in the United States.
Okay, so what do you work on?
So I'm a theoretical physicist. I work on a number of different scales, but much of what I do is focused on gauge invariant prediction. Which means that it's the really predictions directly related to observables, which is hugely important for us to have a framework where we can be talking about observables that doesn't matter how we're telling the story. It's just really focused on predictions. And so we're part of a community that is named after one of its most friendly building blocks in flat space-time, which is scattering amplitudes, which is, at the heart of particle physics and collider physics, the idea of bouncing particles off of each other, measuring what comes out in a physical invariant way. But this field reaches out and touches all sorts of areas, bringing this focus on gauge invariant observation. It's just a very prediction-forward way of doing physics.
So what makes it particularly exciting to you?
Okay, so what I love about this is that when you're focused on predictions, right, and not the stories of how you tell the predictions, when you really focus on predictions, you can be incredibly creative on how you arrive at the predictions, as long as you can verify that you're getting the types of predictions for the types of theories you want to be getting predictions for. And this allows for a tremendous creativity and a utility in terms of, so one way we measure how well we're doing, how we're improving, is whether our efficiency of being able to extract predictions from the theories we want to talk about increases. If we're able to do what would previously unimaginably difficult problems trivially on a blackboard, that means we've gotten better at the language of invariant prediction. And so what's exciting for me is personally, I love to learn about new phenomenon. And this gives me an excuse to take some of the tools and skills I've learned asking questions in one domain and start learning about entirely different domains.
Okay, very cool. Can you tell us a bit more, I guess, about how it started? What was your journey in physics that brought you to where you are now?
So I've always been interested in science. Even as a kid, I was always interested in, stories and learning how the world works. I really enjoyed mathematics when I was young. I loved calculating. I loved numbers, and I very early on I got very interested in programming and algorithms and sort of creating universes that were logically consistent. The thing with programming after you've been doing it for a few years, especially, you know, when I was a kid, it was only as interesting as the problems I was working on.
Yeah.
And that's when I got really serious about mathematics, and I pursued that with a passion through my childhood, through high school, and I loved it. And it felt very ephemeral. The more advanced mathematics I was taking as I was, you know, going into topology, or going into it was beautiful. I loved the structures, but it felt as I said, it felt almost light, effervescent, and then I ran into a computational physicist at the North Carolina Supercomputing Center, and we started talking about what he did and what his life was about. This was, maybe I was a junior in high school, and I realized that in physics, I could play with the math I wanted. If I wanted, I could simulate things. I could apply all my computational skills to trying to disentangle puzzles. But at the end of the day, the puzzles I was approaching would be meaningfully grounded in the world. And that was just amazing. This, especially existential angst of being a teenager, realizing you could pursue something that did have meaning, like trying to understand what was going on in this universe, was very exciting for me. And so then I got into a very good school in the United States to study physics. This is Caltech, and I got to work with all sorts of amazing people, all sorts of different fields. My first project as an undergrad, I was working with a condensed matter experimentalist whose name is Nai-Chung Ye, and she's a phenomenal experimentalist. And one of the things she was doing was probing the properties of superconductors with these little these sapphire microwave cavities. And she was trying to optimize the quality of the sapphire microwave cavities. And so what I did to try to help her out was use the supercomputer at JPL actually to run a finite element analysis, exploring the effect of various topologies, various shapes of these resonators and how that would affect quality. I worked with a high energy experimentalist, Alan Weinstein, who later went on to work with LIGO, but at the time he was very excited about CLIO data, and so we were talking about parity asymmetry violation. My first paper was actually with astrophysicist Roger Blanford and Nick Scoville, looking at gravitational lensing. And I worked with Sergei Bravi, a postdoc, working with John Preskel in quantum information. So I had an opportunity to work on all sorts of different projects that were incredibly different and didn't have anything ultimately to do necessarily with, quantum field theory or high energy theory or cosmology. But I think one of the secrets is that any project you end up working on, any problem you end up working on, ends up being a superpower later on that gives you just your own distinct perspective on approaching things.
Yeah, okay, so that's obviously an incredible breadth of things that you did in undergrad. And then you went on to grad school. Yeah, how was that?
Grad school was amazing. Well, so I should point out that I actually took a number of years off in the middle of undergrad, and worked in industry for a startup company that my friends who were older than me and were computer science majors were ground floor team doing development, and they needed somebody who could play around with data because they were generating a lot of data, and so and I needed some money, and so I think it ended up being something like 8 years. Wow. Or something, and we were incredibly successful. The company we were doing, but we did one thing, and that was providing providing sort of commercial search results. And this generated a tremendous amount of data. And it looked like we would always do well as long as the competitive landscape didn't change. And so they were interested in building out a data science team, a machine learning data science team, to play around with this data and see if we could leverage it and explore potentially new business models from the data. It was tremendous fun, but at this stage, I hadn't had quantum field theory yet. I hadn't had general relativity yet. And these were all reasons that I'd actually wanted to go to Caltech in the first place. And so it was time to go back. And so I went back, and I had my first quantum field theory course, and it was this was from Mark Wise, and it was awesome. And you know, I knew that I could make a living if I had to. And at this point, my wife and I had got married, and you know, and so we were building a life together. But there was still more I wanted to learn if I was able to. And so, you know, I applied for grad schools, and I got into UCLA, which would give me the opportunity to work with Zvi, who was famous, even to me, I knew he was famous for his precision QCD calculations. And I was really excited about that. I was really excited about the ability to calculate, to extract predictions from theories, and the opportunity to learn how to calculate from you know, one of the best in the world was so attractive to me. It seemed like that would be the ideal path for me, and I was sure I was going to spend the next, you know, N years as a graduate student learning how to do very intricate calculations in QCD. So I was very excited to go work with Zvi. What I didn't know is that Zvi had this secret passion for supergravity, and he'd been thinking about it for years and years and years, building up a head of steam to go after a 3-loop calculation in the maximally supersymmetric supergravity theory.
Can you tell us a bit more about what that exactly means?
So there's the standard lore, especially this is a thing that people would speak about a lot, like 20 years ago, is that quantum mechanics and general relativity have no business speaking to each other. They're just incompatible. And you know, if we're ever going to have some theory of everything, it's going to have to be super exotic. It's going to be very strange. It'll upend everything. And what this is based on is something that is very true, which is that if you take Einstein's general theory of relativity and you start calculating quantum corrections to it as a field theory, what you'll find is you'll run into divergences, an increasing order of quantum. So your ability to make predictions breaks down. So a very old way of thinking about this is that this signals that it's a sick theory, that it's no good, that it's incompatible. But what we learned in the 70s was from Wilson, was what this really means is that general relativity is a theory that's effective to very particular scales, right? But then when you go beyond the realm of effectiveness, it starts to break down. You need some sort of ultraviolet completion. So we have a word for theories like this. They're called effective field theories. And that's a formalization of the way we've always done science, the idea that we do science with the nouns and verbs relevant to the scales at hand. If we're going to go surfing, we talk about the glassy conditions of the waves. We don't necessarily talk about the properties of the molecular properties. We're talking about what's relevant. And so the idea, but then there's still a very open question, which is whether all normal quantum field theories of gravity have to be effective in 4 dimensions, or can some of them yield finite results perturbatively to all orders? Do they all have to be effective field theories? And the best candidate for checking something like this, for a couple of reasons, one because of technical simplicity, and the other because the more symmetry you give to a theory, the better its ultraviolet behavior tends to be, would be sort of the gravitational theory, with the most symmetries. And this is called maximal supergravity, or in 4 dimensions, 1 time 3 space, it would be n equals 8 supergravity. And you know, there have been a long list of predictions of where the theory might diverge, ranging from some people predicting, you know, the 3rd order in quantum fraction are 3 loops to 8 loops to 11 loops, but without explicit calculation, it's very unclear how this question would ever be resolved. And there was increasing evidence that Zvi saw before I got involved, actually Henrik and I joined the group at the same time as a close collaborator, Henrik Johansson. Yeah, before we got involved, they started looking at behavior of the theory under very special conditions that would be suggestive of probing at higher loops, but that would be easier to access. And rather than seeing worse and worse behavior, they saw amazingly better behavior the more the more legs, the more moving parts they let play, which motivated actually rolling up sleeves and going after what at the time seemed an incredibly difficult calculation. This is 3 loops, the 3rd quantum order, but yeah, and so that's how I got involved. And the fascinating thing is that getting better at QCD calculations is how we were able to go after these higher loops in gravity theories.
And so in the process, you made quite the discovery, didn't you?
The only reason we were able to go after 3 loops in this theory with so many moving parts, and so just to let you know how many physical states are in this theory. So just gravity in 4 dimensions has 2 physical states. You can have a plus polarized graviton, negatively polarized graviton, but or plus helicity or negative helicity, but the maximally supersymmetric supergravity theory in 4 dimensions, you have 256 physical states running from scalars through fermions, through vector spin 1 like photons, gravity photons in the theory, and gravitini. So you have all these different states swimming around, which makes it sound like it's a much more difficult calculation to do than Einstein-Hilbert, where you just have gravity running around. But it turns out we learned a fascinating lesson from string theory in the 80s. So string theorists in the 80s, Kawai, Llewellyn, and Tai, realized that at tree level, you could describe closed strings in terms of sums over products of open strings. What's interesting about that, in stringy theories, closed strings encode gravitational interaction, and open strings encode gauge interaction, like photons or QCD or Yang-Mills. And one of the nice features, perhaps the nicest feature about string theory, is if you take the low energy limit, you recover familiar particle theories like gravity and like Yang-Mills. Or in this case, like maximally supersymmetric supergravity and maximally symmetric Yang-Mills. And so by taking the low energy limit at tree level, you can go after semi-classical predictions in this gravitational theory by going after semi-classical predictions in the gauge theory. And one of the things that Zvi and his collaborators, Lance Dixon and David Kosauer, did in the 90s was realize that you could really pry apart very complicated loop order calculations into much simpler calculations involving trees, and involves a little bit of bookkeeping, but you can recycle these classical results to build quantum results. And since we knew how to relate classical gravity to classical gauge theory, we could recycle doing loop level or quantum gauge theory calculations to build quantum gravity calculations, even in this very complicated theory. And as I said before, all this symmetry actually makes calculations much simpler. So in this gauge theory, only a fraction of the graphs you might need to calculate in QCD actually show up. And then you could cut them into trees and manipulate them and build back up gravitational theory. So it's a little complicated, but definitely doable. And so over the course of my PhD with Zvi and with my fellow PhD student Henrik, we started building up these increasingly higher order calculations in gauge theory and gravity theory. And this was at a time period where all sorts of people all over the world were doing exciting calculations in these theories, and sometimes in simple limits. So for example, this maximally symmetric gauge theory, this thing that's like a simple version of QCD, you can consider an even simpler limit where only planar diagrams contribute. And when you do so, you see that there are additional symmetries governing the behavior of these guys, and they're visual. So you can draw pictures, so you can calculate increasingly higher loop orders just by drawing funny little pictures with these guys, and just by drawing the lines in the right way, then you'd have your answer. And that only worked for the planar theory, but it's inspirational that maybe by staring at the planar data, you could observe other patterns. And in fact, by staring at the predictions in 3 loops and 4 loops in this maximally supersymmetric Yang-Mills theory, we realized that there was a hidden structure, a hidden pattern to how these pictures contributed to physical predictions. And in chasing down this pattern, we realized that that the building blocks of gauge theories generically, even at the semi-classical level, had very special properties relating to how they conserve charge, or as we call it for gauge theories, how they conserve color. But what I think the simplest example that people would probably be familiar with is the fact that there's the most familiar vector theory that we all learn about very early on as physicists is electrodynamics, and this is Maxwell's theory of electrodynamics, and it's spectacularly quantized as quantum electrodynamics. And one of the things that makes this theory so simple is that the photons don't speak to each other.
Yeah.
But this doesn't describe every gauge theory. And in fact, our most exciting gauge theory, like quantum chromodynamics, the vectors, which are called gluons, absolutely speak to each other. Even classically, they speak to each other. They have interactions. And the way these interactions evolve in terms of color charges is governed by an algebra. It's called the Lie algebra. That is mimicked, it turns out, by the actual dynamics, the kinematics of these theories.
So what you're saying is that there's some kind of duality between the colors and the...
That is what I'm saying. Yeah, and you can exploit this, and you can exploit this duality to promote the gauge invariance of telling physical stories about gluon scattering. You can promote that gauge invariance to the diffeomorphism invariance of graviton scattering.
Okay.
Yeah, and we learned that not only could you do this at tree level, but you could do this at loop level, and the community as a whole learned that you can do this in all sorts of different theories. And in fact, string theory, which originally inspired these KLT relations, you can describe as a field theory double copy between a scalar theory that carries all the stringy corrections. So all the complicated stuff goes to this nice scalar theory, and you can field theory double copy that with just normal gluons and get open strings. which has been very.
So all this stuff eventually led you to something called the color-kinematics duality, right? Can you tell us a bit more about that?
Sure. Well, you're asking at a great place, because this workshop that we're at is called QCD Meets Gravity, and in a very real way, it arose from a lot of the discoveries that our whole community has been playing with for decades now. One of the exciting things that happened while I was a graduate student with Zvi and Henrik is that we realized that there was a story for talking about gravitons where very realistically, graph by graph, you could think of gravitons as behaving just like gluons, but whose gauge group was the dynamics of gluons. That sounds a little bananas, but I can explain it, which is good. So the way photons work is photons don't speak to each other, and this is why we can have our conversation with the radio from the mic propagating, the lights passing through, and they're not interacting at all. But the best gauge theories, like the ones governing the heart of nuclear interactions, the vectors, the gluons, these generalizations of photons, they do speak to each other, and they speak to each other in really interesting ways. And rather than carrying a boring abelian charge like electrons or protons, right? These guys carry interesting charges that have many properties and that interact with each other in a way that's very analogous to the way that rotations interact with each other. You can build a rotation in one direction by combining rotations in other directions. And so we talk about the dynamics of gluons being governed by a gauge group. And a gauge group is just a fancy way of talking about the symmetries of how these charges interact with each other. Well, in a very real way, diagram by diagram in QCD calculations, you'll dress each fancy picture with some kinematic weight, some kinematic numerator, and some color weight that's encoding the way that charges flow through the diagrams. The charges, as I just said, they speak to each other in a very particular way, and you can mimic the way they speak to each other in terms of the kinematics. Now, the fact that the color charges speak to each other in an interesting way is what allows us to tell stories that don't depend on how you're they make predictions, gauge invariant predictions that don't depend on how you're telling the story. And so gauge invariance for gauge theories comes very much from the fact that these color weights play with each other in a very particular way. But you don't actually need them to be color weights. If you were able to have the kinematics of gluons play in exactly the same way, if you had a duality for the kinematics and the color, you could rip off the color, replace it with kinematics, and still have something that's gauge invariant. Except now you've got a spin 1 with a spin 1 in such a way that you're actually talking about something that's spin 2, and that's gravity. And it turns out that this holds to all multiplicity at tree level, and you can use this to derive the KLT relations that we got from string theory. But you can also apply this at loop level, and this has allowed us to go much farther. And as a community, we found that many of our theories that you can pry apart into this way of building blocks that obey each other's structures. And so this goes under the description of a double copy. You have two copies of building blocks that play in the same way.
So the original one you found, I mean, it's known as the BCJ double copy. You're obviously the C in here, but since then it's spawned a lot of other types of double copies that have had many applications in the field of scattering amplitudes in other ways. Can you tell us a bit more about that?
Well, so good. So the fact that you can talk at this semi-classical level about the scattering of gravitons in terms of the scattering of gluons really does beg a question. Can I talk about solutions to the classical equations of motion for gravitational theories in terms of solutions to the classical equations of motion of gauge theories? And the answer is absolutely. And so there have been all sorts of fantastic work all over the world. So one of the most exciting realizations occurred when Donald O'Connell and Chris White and Ricardo Monteiro realized that you can talk about Schwarzschild black holes and rotating black holes and all sorts of special classical solutions make this sort of double copy structure manifest at the level of classical equations of motion. And yeah, the field has just ballooned since then, especially in the advent of gravitational wave observation, which at least gives us classical gravitons that are incredibly relevant to a whole field of astronomy, gravitational wave astrophysics. And so this has injected a tremendous amount of energy into the community, as well as providing a place to touch data. So we've always had the QCD side to be touching data, but now we have also, at least with the h bar goes to 0 limit, a classic limit, a gravitational side we play with. And I think one of the exciting sort of future opportunities for the field that's absolutely manifested at this conference is the possibilities with cosmology, because we're in this realm of precision cosmology, and early universe physics gets to energy scales that we can't possibly duplicate here on Earth, and non-trivial gravitational interactions very relevant in early universe physics, as are the types of effective field theory techniques to extracting that early universe physics from the data that's going to be coming available to us. So this conference is actually incredibly well posed for bringing together multiple communities.
So how did it feel to make a discovery like that, which I mean almost spawned of its field of its own, like the moment itself?
Well, so good. So I mean, the thing about being a physicist, especially being a theoretical physicist, is you're always doing it because you want to learn about the universe, and maybe you'll learn about it in terms of toy examples at first. Maybe you'll spend your whole life only learning like very special features about toy examples, and one of the most fun ways of calculating is not to just brute force follow a machine, but actually to take a guess based upon everything you know about the system. And if you can take a guess and then check it, because verification is almost always easier than construction. If you can take a guess that shortcuts a lot of the work and then verify it, then you're golden. That's a great feeling. That's and that's one of the things that's actually a secret to how we do all sorts of things is just by taking a big guess and then fixing it so that it's absolutely guaranteed to hit where we need it to go.
So if I asked you the question, what would you say is more valuable, to have knowledge in a broad range of topics, or to know one topic specifically?
Well, I think so. Nima likes to say and this is Nima Arkani Hamed. He likes to say that there are as many ways of doing amazing physics as there are amazing physicists, and that's absolutely true. And so I don't think there's one golden path towards realizing something. I think there's some universal lessons that in general, it helps to focus on things. It helps to solve problems. It helps to care. but it really helps to be optimistic. And you can learn as much by trying something that doesn't work as you can by stumbling into discovery. I think, yeah. So I don't know. Yeah, I think yes, that there is a value to doing many things, but I think there's also value to doing them deeply.
Okay. I guess one final question before we have to head out here. Do you have a long-term goal / big picture of what you'd like to realize with your career, or is it sort of a step-by-step, day-by-day?
I think, I genuinely don't tend to think in terms of like career objectives. I do tend to think of science objectives. I tend to think of the types of questions I'd love to be able to answer. I'd love to be able to make certain questions that I can right now talk about in an ambiguous way. I'd love to be able to make them very sharp. I think one of the...
An example?
No, because they're very ambiguous. But Jen, I think this is also something that you learn as you progress, is that we all get we all get better at doing things technically. I think one of the most exciting things is asking the right questions, and that's something we help each other do. That's why we come to conferences like this one, is to find exciting questions that with each other that we can engage in.
All right then. Thank you so much for answering these questions.
It was a pleasure meeting you, Matthias, and what a joy to have this conversation.